Recording. Okay, so today we have seventh lecture. I'm counting them, and I'm not sure, Nikita, if you had chance to look at the videos from our previous lectures. Did you see the videos from lecture 6, lecture 5? It's a pity because I have to continue, and probably you're not gonna understand what I'm saying. Chapter 4 is solving ordinary differential equations. Cauchy's problem. So. Charaskon, what is Cauchy's problem, and what is an ordinary differential equation? Can you tell Nikita?
Problem we now start some starts parameters.
Ordinary differential equation of the first order. Can you tell me what to write if I want to write an ordinary differential equation of the first order?
Plus
Let's take u as a by t plus u. Let's take it in the most general form. Some unknown function, some known function, which depends on time or some independent variable, and the solution itself. That's it. So this is the first order ordinary differential equation. What is the Cauchy's problem for this equation? Or initial value problem?
The u from 0 equal to 0.
Well, let's take an interval from A to B, and then u of A on the left end of this interval is equal to some known quantity. So this is our initial value problem, and we are continuing to speak about the solution of such problems. We discussed several methods already, and the simplest method was called what?
Cauchy?
No,
No,
the simplest of the methods that we considered before. It was Euler's method, very classical method from 18th century that Leonhard Euler developed in 1775 approximately. 1775. This method says that the next approximation or approximation to the unknown solution at the next time point is equal to the previous value for the unknown function plus some time step multiplied by the right hand side computed at Tn yn. And this is the simplest procedure we can imagine. Okay, so I'm not going to repeat all the theory that we considered before. Please watch the videos. Today, what we need to do is to discuss paragraph number 5. If I'm wrong with the number, please let me know. Okay. But I think it should be paragraph number 5, which will be called Convergence, Approximation, and Stability. So, when we formulated all different methods to solve the initial value problem, we didn't say much about why we think this approximate solution will be close in some sense to the exact solution of this problem. So we we discussed a few points in this direction when we estimated the error for the explicit and implicit Euler method. And we found that, for example, for the explicit Euler method, the order of magnitude of the error is O capital of the time step to the first power. And we also discussed that this is better, this error is better, is smaller for the trapezoidal rule, for example. And we also considered a two-step method last time. It also has accuracy with tau to the second power, like this. Trapezoidal, two-step, explicit. They are better. And but in general, we did not develop a theory that allows us to say that the new method that we can develop is accurate or more accurate or less accurate than the previous method. And today I'm going to introduce some very general theory or very general definitions related to not only the Cauchy's problem but many other problems that are solved on the meshes. So let's introduce an operator L, which we'll define this way. This is just the equation that we had with all terms translated to the left-hand side. Okay. So this is this L defines some procedure that we should apply to the unknown function u. And we also include the initial condition to this L operator. Oh, I should have written T0 and T here. In this context, it's going to be more convenient to discuss T0, the initial moment of time, and some moment of time up to which we want to know our solution. Okay, so and we need to introduce another vector. It will be a vector which is 0 for, this is true for t more than t0. The equation describes the solution at time moments that are more than the initial, and this is t equals t0. So the right hand side, we are just rewriting what we had here actually. T0 here, 0 here. So we're just making our problem statement more general. And I'm saying that you can introduce any other differential operator here instead of this particular formula. It can involve second, third, fourth derivatives. It can even be dependent on many spatial variables. It doesn't matter much. The rest of the theory in this part of the lecture will remain the same. What we actually did when we introduced this method to compute approximations to our unknown function u. We actually approximated this operator using some mesh. So we introduced the mesh in time domain. T1, T2, and so on. And we described an algorithm that lets us get the next value of u of y having the previous value of y. We can formally say that we are introducing an approximation operator for this L. An operator L tau. This operator will depend on the time step. Time step is this guy. And this operator L tau will act not on the exact solution, but on our mesh solution. So this sequence yn plus 1, yn plus 2 defines a function y tau, which we called, no, I shouldn't write this. It's here. I should write like this. Yn is a function from 0 to n capital. So this mesh function is just a set of values yn computed using this procedure. Okay? So we can think of this table as a function. And we are saying that this approximative operator for L acts on this whole mesh function. And in the most general form that we introduced in the end of the last lecture, this operator can be represented as follows. It is 1 divided by the time step, and here we have a sum. If we are using a k-step method, here we have a 1-step method. But in the second part of last lecture, we discussed that we can use also 2-step method, and it can be extended to k steps. So if we are using a k-step method, then we can say that here we have minus j, the general formula, minus some function phi capital that actually involves the right hand sides. And it will depend on the new value that we want to know. The new value that we want to know is always yn plus 1. Okay? And minus k, yn plus 1 minus k minus 1, and so on, up to yn. And maybe this function may also depend on n plus 1 itself, as we've seen, for example, in trapezoidal rule or implicit Euler method. And what else? What is the other parameter that influences this phi? It is also tau, because because this guy, or in trapezoidal rule, what we have here, tau by 2 f of tn yn plus f of tn plus 1 yn plus 1. Right? So this is an example of phi. Trapezoidal rule gave us an example of phi, how it can look. And you see this depends on tau, actually. And you can also see this here as well. Let me check. Yes, I have to divide it by tau. Yeah, anyway, I should write it. It's not phi. Phi is here. This is phi. In this particular case. For the trapezoidal rule, phi will be 1/2 multiplied by this sum. Okay? Do you see it? Is it clear? Nikita, what I'm saying?
Maybe.
No, it should be clear or not clear. If it's not clear, I will explain it again. So, this is just a generalization of several methods that we already considered. This method that I'm reproducing here is called trapezoidal rule. It takes two values of the right hand side at point Tn and point Tn plus 1. The Euler's method took only one value of phi, of f, only at Tn. In more general form, the sum can involve k components in k previous steps. Okay, I hope you will understand it when you watch the lecture again, or maybe watch the previous lectures. So, what we should add to this operator? We should add the initial conditions. Initial conditions are also present here. So, yk plus yk minus 1. These are the quantities that we need to know to start the k-step method. y0, y1, yk minus 1. The number of these guys is k. Okay, so this is the approximation of this operator. And next, so we have two problems. Original problem. Original differential problem. L nice is equal to F nice. This is the original differential problem. And the second approximation to this problem, or discrete analog. L tau of y tau is equal to, I didn't introduce F formally, so F tau will be 0, and just the values that we assign to the initial points, at the initial points. So these are the initial values that we always have. They go to the right of the equation. Okay? So this is an approximation of this. And I'm saying that under this L you can substitute many other different differential problems, and under this guy you can substitute all the family of different methods to solve a particular differential problem. Okay. Now we want to formulate what we understand by approximation properties of this method. How we define that the method approximates the original problem, and how we define the fact that this mesh function converges to the exact solution. So 3 definitions will follow. When are you here? Okay. So we'll have the definition number 1, which says what convergence means. Convergence of the approximate solution to the exact solution. Definition 1. The solution y tau, let's call this problem star and this problem 2 stars. The solution y tau of the problem 2 stars converges to the exact solution of the problem star if the following inequality holds true. I will write it down and then discuss what it actually means. Y of t, I want to stress that this is a continuous function of my time variable. We'll discuss what this means in a second. So let's look at this statement and see if you understand it or not, the actual meaning of the statement. Do you have questions? Is it clear what it means? Or how to calculate this norm if you know u? How would you calculate this and check whether your problem converges or doesn't converge? Whether your approximate solution converges to the exact solution or doesn't converge, if you have u. Suppose this is your integral curve. This is the exact solution, u of t, which is usually unknown, but we can take some problem for which it is easy to write this exact solution. And we can play with this problem. We can use the method that we chose, for example, explicit Euler or implicit Euler or trapezoidal rule, to calculate the set of values defining this mesh function. I'm saying the set of values, and it's important to understand that it's not going to be a continuous function, but only a set of distinct values. Let's call it Tn, Tn plus 1, and then what we have, I need another marker. For example, with Euler method, we start from estimating the derivative, and we write a tangent line to the actual solution, to our exact solution. Tangent line. Then we continue this procedure on and on. Right? So we should get something like this. And this is going to be our y tau. Our function y tau in this particular point Tn. It's going to be defined by the value yn. In the next point, it's going to be defined by the value yn plus 1, and so on. So, what this relation says? Can anyone explain how to interpret it, this relation, or how to calculate this norm?
If we
my question is, you have some mathematical expression here.
Yeah.
Can you sit down and program and write a program to calculate this norm, the value of this norm? Because we need to be able to calculate this norm if we want to check whether it converges to zero or not, right?
Can we use from the graphic equation? Because we use the method.
So you can explain on this plot how you would calculate the norm.
No.
What this norm means? Are you familiar with norms at all? What we mean by norm? When we say norm, what it means? For example, if we had two functions like x squared and y of x, y1 of x equals x squared, and y2 of x equals and I would ask you to compute the norm. For example, x is from 0 to 1. X changes from 0 to 1, and I want you to estimate the norm. What would you do to tell me what the norm is?
Zero, zero to the zero, zero.
What's that? What's that? Could you say it again?
Zero,
Point
zero, dot,
one.
zero, zero, one.
Why? This is the function x squared.
Right.
This function will be above or below the previous one? Below. That's good. What's going to be the value of this function at the point x equal to 1? This is 1. What's going to be the value of the function? I hope this function will have the value 1, right? And how about this blue function? What will value it will have? I'm exaggerating the difference for sure, intentionally.
You have 2 points and just the line.
What is this value?
Really?
Yes.
If you put all
Well, we just substitute 1 here, right?
right.
Square it.
All 9. All 9. Right.
This is the value, right?
Right.
Okay.
This is the first, yes, for the previous one. For the second one is the 1.
First function has
Yes.
this value, the second function has this value at the point x equal to 1, right?
Right.
So, what is this norm? What does the norm mean? What's the concept of norm in mathematics mean at all?
So it could be.
Can you explain?
Can we just draw a line through this between 2 points?
Draw a line between these 2 points.
Yes.
Monsieur.
Maybe it's the norm.
Well,
Or
the norm. This is something you should grab from your mathematical course. The norm is a way to say if 2 objects are close or far from each other. This is the meaning of the norm concept.
Okay.
And we can define this norm in many different ways. For example, one of the ways is to calculate the maximum difference between y1 and y2 on the interval from, say, 0 to 1. On the interval where we consider these functions. Okay, we can just take the maximum, and we see from these particular functions that the maximum will be on the right side, not on the left, because on the left they are both 0, and on the right they have the maximum difference. So this will be the value of this norm if we choose to calculate the norm this way. We could choose to calculate the norm a different way. How? For example, we could take an integral, not the derivative, an integral. So we could integrate the shape that sits in between these two curves. For example, but usually mathematicians do the following. They square the difference between the two functions to avoid negative influence of the negative values. Okay? And they say this is another formula for the norm. This norm is called L2 norm. No, I don't know if you had this notation in your mathematics course or not. This is a Lebesgue norm, a second norm. This is just a square, integral of the square of the difference between two functions. I hope you can see that the value, the actual number that we get, will be different if we choose this way of computing the norm or this way of computing the norm. And there are many other ways of defining the norm. It doesn't matter which way you would take, but you have to fix the algorithm of the norm computation and stick with it. Okay? And in general mathematics course, they also discuss what properties this algorithm must satisfy to be valid as a norm, to be a valid norm. The properties are there are three properties. They are very simple. I don't want to teach you mathematics today. Just wanted to recall. So when we try to compare function y, tau, and function u, we should feel, or you should feel, a problem. This function y, tau, is only defined at a distinct number of points. It is not a continuous function at all. Y, tau. Do you see it? While u of t is a continuous and differentiable function. And this means that you couldn't just take this expression, because the integral, the difference will be only at some finite number of points. And in all the other points, the difference will not be defined at all. So you want to be able to integrate. Before computing the norm, we have to do something with our continuous function, for example, to make it comparable to the finite set of values. And this is, what we do is defined by this square brackets. It is called a projection of our continuous function onto the finite dimensional space of our mesh. How to calculate this projection? The simplest way is just to take the values of u at these points, but it's not the only possible way. This is the simplest way. You could choose to take for the value of u at point n, you could choose to do the following, for example. Take 1/2. Nothing prevents you from doing this. And this will also be a projection of this continuous function onto the mesh. You see? I'm saying it very slowly, because these facts might seem trivial, but they are not trivial because of these considerations. It's not the only way to project the function u. Okay, but to make it simpler in your mind, you might think that we just calculate u at some points. Okay, so what is the norm? The norm, we can define it as the maximum between yn and un. Well, if we call un the value of u at point n, for all n from 0 to n. So this guy must tend to 0 as the mesh size, or as the step size tends to 0. If it holds true, then we say that our approximate solution converges to the exact solution.
How do we check it?
Yes, this is a very good question. How do we check it in the situation where I deleted our initial problem? In the situation if we don't know the exact solution. So this formula can be used only if you know u of t. But if we know u of t, why are we sitting here? What are we doing here? In most cases, you would not know u of t. And that means that you need to develop some theory to evaluate this quantity through other quantities that you can calculate. So this quantity cannot be calculated in a real situation. You see it? Okay. And I forgot to mention one other thing related to the previous definition. So if this holds true, and moreover, the following relation holds true for some p more than 0, we say the convergence has order p. This is what we mean when we say that some method or some approximate solution converges to the exact solution at order p. You remember I wrote O capital of tau to the power of p. This is exactly in terms of this definition. So, second definition. Second definition will give us something that we can actually check in any real situation. And we will check it before we start to solve the problem. This will be the property of the method that we choose. The problem, 2 stars, approximates the problem 1 star. So the finite dimensional algorithm approximates our original problem if, how would you define the approximation property? So approximates means that this problem is close in some sense to this problem. how would you define it? On its exact solution. Sure, on its exact solution. If okay, silence. No one tells me how to define it. If the following holds true, suppose I have this exact solution. If I substitute this exact solution in my approximation, problem, so I put the exact solution projected to the mesh, to my approximate solution. But this equation will not hold true any longer. Why? Why am I saying that? Why this is not going to be zero?
It's not gonna be zero
Why?
because it's an approximation. Maybe.
Yes, but because what we did to approximate the derivative, for example, we used a finite difference formula to approximate the derivative, or we approximated the integral using some a formula that is not exact, right? That's why when we put the exact solution of the original problem here, we shouldn't expect to get zero. It should be some vector. It will be some vector r that depends on the time step. And it's not zero, not a zero vector. But if we can prove that this property holds true for this vector, if its norm of the vector tends to zero when the time step tends to zero, then we can say that when we make the mesh denser and denser, when we take the time step smaller and smaller, we will get the same problem, actually, in the limit of small tau, right? And moreover, parallel to this addition to the previous definition, we have the same addition here. If this norm if for this norm this inequality holds true, then we say that the problem 2 stars approximate the problem 1 star at order p. At order p. Good. So, let's think about this. Let's imagine that L tau represents explicit Euler method. Very simple story. Explicit Euler method. And let's think, how would we check that the explicit Euler method approximates the original problem? What would we technically do? We need to invent some toy problem or a set of toy problems for which we know the exact solution.
Yeah.
Right? And we play with our explicit Euler method and substitute those solutions to the formula and check whether this vector tends to zero for this particular method or not. If we prove that the method we choose obeys this property, and if we are able to say what the P is, then we know that our method is expected to approximate the original problem at order P. And this is good. But it's not all. Because this is different thing from the convergence. We did not prove convergence. The method may approximate the original problem, but the approximate solutions still not converge to the exact solution. We need something else to connect this good approximation property with this wanted convergence property. And this something is called stability. We need that our approximation method is stable. What means stable? We'll define it in a second. But from your previous experience, what you call what process can you call stable? How would you define the stable process in physics or
It's a
chemistry?
constant.
Hmm?
It's a constant.
Constant is good, but it means that nothing happens. For example, you have a chemical reactor. Let's think of a chemical reactor. As an engineer, what property you want to have from your chemical reactor? When you put, let me think of a particular example. So if you put hydrogen and oxygen, and you oxidize hydrogen with oxygen, can you imagine how it looks? Nikita, can you imagine how oxidation of hydrogen with oxygen looks? It's a bomb. But suppose we want to have a slow and controllable process. So stable is a synonym to controllable in this sense. So there is a technology called fuel cell. If you heard something about that, do you know about fuel cells?
Fuel cells?
Топливные ячейки. Fuel cell technology. The technology that is under development still, but there are working examples. It oxidizes the hydrogen slowly so that the process is controllable, and the whole device that makes this oxidation can be packed in the typical accumulator size. So the idea is to substitute our lithium ionic accumulators with these fuel cells, because it is very attractive. Hydrogen is relatively cheap, and oxygen is cheap, and they are very energy efficient. So if we can control this process and avoid this device to become a bomb, then we would be happy. What we need is stability, meaning that small change in initial conditions should lead to small changes in the result. We should never have the situation that we touched something and we got explosion as a result. Okay? So this is the meaning of stability. And now let's talk about mathematics related to this concept. At what time should we stop the first part? 11:20, 11:30, I don't remember, 11:20 at least. Okay, I have some time to formulate the stability definition. So, definition number 3. So we say that problem 2 stars is stable if for 2 mesh problems L tau of V let's call it some so we just put some vector here, some mesh function, and put some other mesh function here, and formulate 2 different mesh problems using this algorithm. If the following is true, what is true? The solutions are closer to each other than some constant multiplied by the sum of these errors. Actually, these are errors. So I forgot to introduce one term. Here, this is called the residual vector. So we say that the algorithm L tau is stable if the exact solutions of these approximate problems will lie closer to each other than some constant multiplied by the norm of this and this error. So how to interpret it?
I don't understand.
So we've seen, so suppose yt is the exact solution of 2 stars, exact solution of approximate problem. But if you choose well, how to say that? If you choose 2 different ways to get your approximate solutions, you will get different residuals. And for stable problems, the smaller the residual, or the smaller the difference between these residuals, the closer the result should be. Well, maybe this formulation is not very obvious for you. Let's try to introduce an equivalent formulation, but this will only be equivalent for linear problems. If this L defines a linear problem, it means that all the derivatives and the function itself must be involved in the equation linearly. No squares, no exponents, no sine, or any other function under which the unknown solution goes, only linearly. If the L is linear, if L tau is linear operator, then we can say is stable if the exact solution of this approximate problem is bounded by the norm of the right-hand side. the smaller is the function that stands on the right of the original equation and approximated later, the smaller is the solution.
Mhm.
Is it more easier to imagine what this means? For example,
Yes.
again, I'm trying to bring in an analogy or chemical or physical analogy. If you have some control system, for example, you have a plane and there is a control system that wants to drive this plane towards the Earth to land it. And the system changes the angle of the wing a little bit, of the ailerons at the end of the wings, to incline the plane towards the Earth. But if the plane is a non-stable system, it might happen that small change in the angle will lead to catastrophic change in the behavior of the plane. It will just flip around and that's it. It will fall down. Right? So it means that small change in the right-hand side is the angle that we use to change the inclination of the plane. For unstable problem, this is not true, and then why the actual angle that plane takes will be very different. Its norm will be very different from what we wanted. This is a physics analogy, so to say, or technical analogy to this concept. Okay, let's have a break.